We are getting there. Okay, so problem 8. So now we're looking at problem 8, which is just what is the pH of 0.1 molar of just weak acid, HNO2, no salt added. Now we're considering what happens to the pH after we add some acid and some base. So the first step, once again, is to figure out the pH of just the weak acid. I feel like we have calculated that before. Maybe we haven't, never mind. Okay. To do that, it would be pH using Henderson-Hasselbalch. I got it. pH is equal to pKa plus the log of conjugate base, which is NO2 minus, over HNO2, which is acid. Why do we know that? Is because we're looking at the dissociation of HNO2 partially dissociating to become H plus and NO2. This is conjugate base, this is acid. So information that we have is, oh, it's somewhere else, that's why, right? Where did I write it? Right here. Great. Oh. Okay. Oh, okay. We remember, okay, we don't have to go through this. We know what the pH is of this. The pH, we did calculate ahead of time, or did before. It was 2.17. So this was from another problem. This was from problem something else. Problem AB6. Or problem AB3. So this is from problems AB3 or AB6. We verified that the pH, this is what we're starting with for just the weak acid. So we got that, right? Okay, second thing. Now we're going to consider adding some hydrochloric acid. And we first look at the dissociation of hydrochloric acid. That's HCl, strongly dissociating, or fully dissociating to get H plus plus Cl minus. And we know that we're given originally 0.05 molar. Don't have anything till it dissociates. The change is that it fully dissociates. So all this goes away to then show up in the products, which then gives us equilibrium concentrations of 0, 0.05, and 0.05. So we know that we are adding, once again, this is the proton concentration that's being added because we added some acid to the weak acid. So then for the reaction with HNO2, the weak acid, we are going to use this reaction here, okay? So initially, let me just move this over, or AB6, okay. So initially, we start with 0.1 molar. Why? Right there. That's what we start with. We have 0.05 moles of acid that we start with because we added it from here. Okay? So that pops in there, and we don't have any conjugate base. The change, it's a weak acid, so we subtract X and add X on both sides. It doesn't fully dissociate because it's a weak acid, like we said. So then our equilibrium expressions are 0.1 minus X, 0.05 plus X, and X. Okay, so now we are not going to use Henderson-Hasselbalch. We're going to use Ka, the relationship with Ka and the approximations to solve for X. So Ka, I know, your next question is, when do we know we can use Henderson-Hasselbalch and not use Ka or vice versa? You can use Henderson-Hasselbalch if you can calculate numbers for all of these values. But if you have an expression for X in here that you need to use, then don't use Henderson-Hasselbalch and use the expression with the Ka or the Kb. Okay? Okay. So, Ka is equal to concentration of acid times concentration of anion over acid. It's not acid, but H plus over here. O2. Got it. All right. So we have this. So now we know the Ka, 4.5 times 10 to the minus 4. We've been seeing that number for a while. So we can go ahead and put that in, which is 4.5 times 10 to the minus 4 is equal to X, X 0.5 plus 0.05 plus X times X all over 0.1 minus X. So I got these from here, from our ice table. So our concentration of H plus is 0.05 plus X. There that is. Our concentration of NO2 is X. Our concentration of HNO2 is 0.1 minus X. Can we make the approximation? Yep. Let's use the approximation. Let's not bother to calculate it because we've already calculated that it would be, if we had the pKa over the initial concentration of 0.1, we know that our approximation is valid because we get a percent dissociation of 0.45%, which we did in like problem 3, I think, or something like that. Okay, so we're using the approximation, which means that these x's are going to go away. Not that x, sorry, this x. Because we can assume that x is a whole lot smaller than 0.05 and also obviously 0.1. So then when we calculate this out, we get 4.5 times 10 to the minus 4 is equal to 0.05 times x divided by 0.1. This calculation is super straightforward. All we do is solve for x, and we find out that our x is equal to 9 times 10 to the minus 4. And this value of x is equal to our concentration of NO2 minus, right? So that's true. Oh, okay, so we are going to use, we are using Henderson-Hasselbalch. Once we know our concentration for NO2, we can go back and use Henderson-Hasselbalch. All right, so pH is equal to pKa plus log of NO2 minus over HNO2. Okay? Right? I just copied it from up there. Now we have values for NO2. Before it was X. We didn't know what X was. So that's not going to work. Hopefully I'm still recording. Okay. We didn't know what X was. But now we do. So we can put in values. So pH is equal to the pKa, wrong paper, pKa, negative log of the pKa, negative log of 4.5 times 10 to the minus 4 plus the log of 9 times 10 to the minus 4 over 0.1. Okay? So we put in pKa, negative log of 4.5 times 10 to the minus 4, which came from here, plus the log of the concentration of conjugate base, which is there, which was X, 9 times 10 to the minus 4, and the concentration of acid, which initially is 0.1, as we see up here. So then we find out that our pH is equal to 1.30. Now, this value is much lower than when we had conjugate base in there, when we had salt, that's right. In problem 7, when we had salt, it only decreased to 2 something. But without any salt, it decreased by a whole lot more. So that's what is one of the takeaways for this.